Hello everyone, today we are going to consider section 7.6 complex eigenvalues and see how solving differential equation, matrix differential equation is different for complex eigenvalues from real eigenvalues. So our first question we are trying to answer is how a solution of differential equation is different from real eigenvalues. Well, let's remind you, general procedure for real eigenvalues was well, let me write down first equation. So remember, if you do have differential equation, which is a vector differential equation, something like this, matrix A and vector x. Here, x is a vector of unknowns, and there are like just two variables, x1 and x2, and A is a matrix, right? So the procedure for real values was find eigenvalues, find eigenvectors, and usually they are linearly independent, and you can use, like if it's matrix 2 by 2, you can use these two eigenvectors as your two linearly independent solutions, combine them together with different constants, and get your final general solution, right? So what is going to be different for the case when we do have complex eigenvalues? I want to consider an example. That's going to be just the fastest way to explain, okay? So example number one, and I'm going to consider a very simple equation, and the matrix is going to be just like 0, 1, -1, 0, and a system is going to be like 2 by 2. So I'm going to build characteristic equation. And characteristic equation is going to provide us with eigenvalues. And I'm going to take a determinant of it, right? It's 0 minus r, 1, -1, and again, 0 minus 1. I'm trying to make it very, very simple one, just to show how everything is working. So we take a determinant of this matrix, and we are going to find that it's minus r squared minus -1 by 1, which is going to be equal to 0, which is actually going to give us r square minus going to cancel each other, and we have r square plus 1, which is going to produce two complex eigenvalues, right? This equation is going to produce two complex eigenvalues. I'm going to move over here. So r1 and r2 are going to be plus minus I, right? We are extracting a square root of -1. Actually, here is r square equals -1, which is going to produce two complex eigenvalues. I'm going to write down complex eigenvalues. Now, normally for a real eigenvalues, we are going to take the first one, plug it into the matrix, find the eigenvector, and kind of multiply eigenvector by exponential function with this eigenvalue, and that's going to produce our first solution, right? And then we are going to repeat the procedure for second eigenvalue, and it's going to just solve, like find for a second solution. We combine them together and get our final general solution, right? What is going to be the difference here? Well, I'm going to start with finding the first eigenvector. First eigenvector. And that's going to be eigenvector which corresponds to r1 equals to I, right? So what I'm going to do? Well, I'm going to just plug it into my matrix and solve it. So let me do it. So minus I because it's minus r over here, right? 1 minus 1 minus I, and that's a matrix, right? And the constants for eigenvector, right? And it's supposed to be equal to 0. You see, I put 0 with a bar because this is not actually just 1 0. There are two zeros, right? 0 on the top and 0 on the bottom. And well, because I know already that determinant is equal to 0, I know that these two rows are linearly dependent. So I actually solve only one of them, considering the one variable as a constant and another variable is dependent, right? So what I'm going to have is minus I C1. So this C, it's actually a column vector of two arbitrary constants, C1, C2, and minus, sorry, it's supposed to be minus I C1 plus 1 C2 equals 0. I'm going to express C2 as I C1 and consider C1 as my free parameter. So C1 is my parameter, like a free parameter, which can be any real number, just because these are under defined system, and one of the variables is going to be a parameter. So, well, usually when we solve 2 by 2 systems of equations, we set it like we call it t, right? And we write down, okay, x equals t and y equals, I don't know, something like 3 plus t or whatever, right? Here I'm going to just keep it as c1, because if I introduce every time t, it's going to be too long. So what I'm going to have, then my vector c is going to be what? C1, which is my free parameter now, and C2 equals I C1, right? And I'm going to take C1 because it's repeated here and here outside of the vector, and I'm going to have 1I over here. Well, because it's just a constant, right? I'm taking it outside, and I'm going to write down my general solution number 1, solution vector number 1. And that's going to be what? C1, 1I, and I have to multiply it by e to the power of I t, right? Why it's I? Because this I, right? That's my agent value. So normally it's supposed to be RT, but because my R is equal to I, I'm going to put I over here. Now, what I'm going to use? I'm going to use Euler's formula and convert this thing into like sine and cosine, right? So I'm going to write down C1, 1I, and over here I'm going to write down cosine of t using Euler's formula plus I sine of t. I'm going to write down Euler's formula. Okay. What I'm going to do next, I'm going to multiply. This is just a constant, right? It does not look like a constant because it has like variable, but it's not a constant actually, just coefficient. I'm going to bring this coefficient inside of my vector. So what I'm going to have, I'm going to continue lower C1, and I'm multiplying or bringing this coefficient inside of the first part. I'm going to have cosine of t plus I sine of t. And if I kind of multiply cosine by I, I'm going to get I cosine of t, and I by I is minus sine of t. Why it's minus? Because I by I is -1, right? And I'm going to use this property. Now, what I'm going to do, guys, I'm going to separate a real and imaginary part of this complex number. I'm going to keep C1 outside. C1 is still outside. And I'm going to separate real part. Real part is cosine, right? Cosine of t, and minus sine of t, and I'm going to keep it together. And imaginary part is going to be I, right? I from here and I from here, and then C1, and that's going to be sine of t and cosine of t. Right. Why I'm doing this? Let me first label them. So this is a real part of my complex solution, and this is imaginary part. So why I'm doing this? Well, I want to kind of escape of solving a second eigenvector. I can do this if I prove a little something which we already proved before, but kind of let's do it one more time. So I'm going to scroll a little bit up so I have more space over here. And I'm going to prove something. We remember from section 3.3 where we were dealing with complex eigenvalues for just linear equation that, well, let me write it down. We remember from chapter 3, section 3, where we were just solving linear equation, just one equation with some like eigenvalues, that if I'm going to write down big X, but actually you remember X is a solution. If solution X can be represented as a real part plus A real part plus B imaginary part, and if this is a solution of differential equation, then A, which is a real part of the solution, and B, which is imaginary part of the solution, are solution by themselves, are solutions by themselves. Instead of self, I'm writing down like alliteration. Come on. Oh, that's too much. Sorry. Well, why? Why are they solutions? Well, remember that if complex number, which is like a plus bi equals to 0, it means that both a equal to 0 and b equals to 0. Otherwise, it's not going to be 0. If complex number is equal to 0, then both imaginary part and real part of this complex number are equal to 0. What is going to happen if you take solution X, like this one, and plug it into differential equation looking like this? X prime, A, X. Just take this solution which is separated in two parts. And A and B here are going to be vectors. So I'm going to do it. So I'm going to differentiate this solution. So it's a derivative of A. A is not just a constant. A is going to be something like this. The cosine, sine, and the constant multiplied by it. B derivative I equals matrix A multiplied by A plus BI, right? What I'm going to do, guys? Well, I just plugged my solution, which is looking like this. Some real part of the solution, some imaginary part of the solution, I just plugged it back into equation, differential equation. Now, I'm going to move everything to the left side in this equation and to write it down like A prime minus A. Sorry, there are two A's here, which is a little bit confusing, but let me write down this A is a different color. This A is actually a matrix. Okay, I'm writing down it's in red to separate from this A, which is like real part. Sorry, does not looks a little bit confusing, but we're going to use it just temporary. So I'm going to maybe even write it down matrix. And this one is just a vector. Let me go back to my blue color, and plus B prime minus AB multiplied by I, and it's supposed to be equal to 0. And again, this A is actually red one, right? I'm going to make it red. This A is a matrix. This B is part of this complex solution. Okay, we remember that complex number is equal to 0 only if both real part is equal to 0 and imaginary part is equal to 0. What does it mean? I'm going to write down them as separate equations. A prime minus A by A equals to 0. And again, I have to change the color of my this A because this A is a matrix. If I separate, if I move back this AA product to the right side, I'm going to have, sorry, I have to go back to my standard color. Why don't I write it down in A like this and back in A like this? You see what we have, actually. We have exactly same differential equation as we have over here. So A is a solution. Oh, sorry, somehow I pressed the eraser. I'm going to write it down. So A, which is a real part, is a solution of differential equation. Well, for B, for imaginary part, I'm going to write down just basically same. B prime minus, and again, I have to change the colors to not confuse you. Oh, did not actually work. let me read it first and then, oh, come on. And back to blue, b equals to 0, which is going to bring me to b prime equals a, sorry, lots of like confusing variables. Well, ab, I can put vectors over here, but because actually this real part is a vector, right? We remember this. So I just did not write it down. Probably that was a solution to not write it down like a different color. This is a vector, this is a vector, this is a vector, this is a vector, and whatever is without a vector, it's not a vector then. This vector, this, and this, which is going to be just like b, imaginary part, is a solution of differential equation 2. So we got 2 solutions. Now I'm going to sum them. We have 2 solutions. To be good, we just need 2, right? But we need 2 linearly independent solutions. And they both are real solutions, right? Because if you drop I from here, like over here, you kind of expel I, you are just going to have like real solution, right? So we can use these 2 real solutions as like our necessary real solution. So you can write down that x solution, general solution, is x1 plus x2. And instead of x1, you use a real part. So it's, you write it down, c1 cosine of t minus sine of t, and c2 sine of t cosine of t. I'm hoping that I did not miss a minus anywhere. Why did I change this c1, which I had over here? Let me scroll down a little bit, to this c2. Well, because I'm not actually using the constant. Constant is just a scaling factor, right? But I'm using actually the vector, eigenvector. I'm multiplying it by a different constant because we remember that these solutions are linearly, well, I'm going to prove it, but they are going to be linearly independent. So I can multiply each by a different constant. And the plus is that this solution is real and this solution is real, which is normally what we are searching for, because, well, imaginary numbers is a good tool to solve equations, but you don't really see imaginary numbers in like nature, right? If you solve something like a real life problem, your solution is supposed to be real. You can use imaginary numbers as a tool to help you to get to this real solution, but your normal solution is just normal, real solution, right? I'll need to show that these 2 vectors are linearly independent. So I'm going to kind of write down what I'm doing. Are they linearly independent? Sorry. So are they linearly independent? Well, I'm just going to check it. I'm just going to check the Wronskian, and it's going to be cosine of t minus sine of t, right? You make up Wronskian just from the vectors. You don't differentiate here anything. You differentiate when you deal with higher order differential equations. Here, I'm teaching you only how to solve first order differential equation, but we are having several of them, right? That's why we have Wronskian, not because that's a higher order differential equation, but because we have several differential equations. Well, determinant is going to be what? Cosine square of t minus negative sine of t by sine of t, which is going to give us cosine square of t plus sine square of t, just because minuses are going to cancel, which is equal to 1, which is not equal to 0. So they are linearly independent. So they are linearly independent, and they are good for us to use. Now, usually people are asking, well, if I was in real class, well, why are we doing all this? Why don't we just solve for the second eigenvector and kind of combine these 2 solutions together? And if you do this, there's going to be no mistake. So if you do a standard procedure for this equation, like find 2 eigenvalues and they are complex. For each complex eigenvalue, you find separate eigenvector. You produce 2 separate vectors, which are going to be linearly independent, and you use them as a solution. Is it going to be better solution or worse solution? No, it's just going to be another solution. Why do we like this one? over that one, which we can get by standard procedure without any speculations about like that imaginary part and real part are going to be solutions, because that solution is going to be definitely complex one. So if you do use two complex eigenvalues and plug them into the matrix, you are going to get two complex eigenvectors. And somebody will ask, okay, we got two complex eigenvectors, we combine them, we got complex solution. Now, how it's going to work if I'm solving a real life problem, like normal, where everything is real? Well, remember guys, we are doing just general solution here. If you are solving initial value problem and your initial values are just normal real numbers, for example, x1 at 0 equals 1 and x2 at 0 equals, I don't know, -1. When you plug them in and calculate the constants, your final solution is going to be real. It's just going to give you all longer calculations, but it's still going to be a real solution. You are going to find a real solution. Here, you kind of do these calculations inside, like once when you prove that imaginary part and real part are solutions. But if you do it like a standard procedure, eventually you are going to do these calculations and you are going to get the very same answer. So this solution as a general solution is going to be slightly different from general solution if you solve a general way with two eigenvalues and two eigenvectors. But when you plug in initial values, and normally every differential equation comes as initial value problem, you are going to get the very same answer. So that's the merging point between like different ways to solve it. I would prefer you to solve it this way, just because it's a little bit faster. You look for one eigenvector. You don't need to prove actually all this stuff. You're just going to solve one eigenvalue for one eigenvector, find imaginary and real parts, and use them as your solutions. I'm going to show you another example of how to do this. I want to change the color, maybe green. Let's do green for my next example. So let me scroll it up. So, well, that's how people are solving it. If you don't like it, okay, you can keep using complex numbers. I don't mind actually, and that's not bad. Actually, if you solve it using, computer system does not care about like we like it real or complex. It works with complex numbers, even doesn't see that are complex numbers. So, okay, I'm going to move to example number 2. Oh, sorry, somehow I don't have let me scroll it up so there is nothing distracting me from it's not allowing me to move to. Well, okay, let's do example number 2. In example number 2, I'm going to solve a real differential equation. That the first one was kind of fake. I created it to show you how everything is working, but now something real. So the matrix is not simple one. It's 3 minus 2 and 4 minus 4. This minus belongs to 2. It's not like 3 minus 2, which is equal to 1, right? So I'm going to start with doing characteristic equation. So determinant is going to be what? 3 minus r minus 2, 4 minus 4 minus r. Well, a little bit more complicated, right? I'm going to multiply crisscross and get like 3 minus r and minus 1. Sorry. Why it's minus 1? Minus 4 minus 1, right? I did 4 instead of 1 actually. I'm really sorry. When I was writing down my system, I put over here 4 accidentally and I started working with 4, but 4 is not going to give me what I want. I'm sorry. So I'm going to fix 4 into 1. It was actually -1. -1 minus r, sorry, -1 minus r, and multiplying these 2 is going to give me +8. Why +8? Because it's supposed to be minus, but there is -2, so we are going to have +8. And if I simplify it, I'm going to get r squared minus 2r plus 5 equals to 0. I'm going to search for roots, r1, r2, and they are going to be what? Plus minus a square root, and I have 4 minus 4 by 5, 20, and plus 2 and divided over 2. Again, it's not the most complicated one, but it's a next level, a little bit more complicated. So what I have minus 16. 4 minus 20 is minus 16. Extract the square root is going to give me plus minus 4i plus 2 divided over 2, which is going to give me 1 plus minus 2i. You see, a little bit more complicated. Now my complex eigenvalue has a real part too. Again, I'm going to stick to my plan. I'm going to search only one eigenvector. I'm going to solve it for eigenvector for R1, which is going to be 1 plus 2i. By the way, if you solve it for 1 minus 2i, you are going to get exactly same solution. Again, up to the point it's general solution, it can look slightly different in the shape with all the pluses and minuses and complex numbers. But when you do initial value problem, it's going to go back to like same one. Okay, so I'm going to plug this one into my matrix. Now it's going to be a little bit more complicated, right? It's going to be like 3 minus 1 plus 2i, and here minus 2, and here 4, and this minus 1 plus 2i. And my matrix, and I multiply it by a vector of two constants, c1 and c2, and it's supposed to be equal 0 and 0. We remember the determinant of this matrix is equal to 0. We were searching the R's which satisfy this, which means there's two rows are supposed to be linearly independent. If you look at these two rows, you are going to realize, I'm going to simplify them a little bit to kind of show it more explicitly, minus 2i, that they don't look like they are linearly dependent, right? Normally, what you see when something is linearly dependent, well, you take row number 1, multiply by some number, and get row number 2. Like, for example, you have 1, 2 here, and 2, 4 here. You multiply the first one by 2 and get the second one. Here it's not obvious, right? To kind of break this kind of view that they are not linearly dependent, I'm going to prove it. But you don't need to do this when you really solve something. I'm just proving it to show you that these two are linearly dependent. Linearly dependent, though it's not visible. Again, I'm going to put in parentheses sorry. Don't again. Sorry. Don't have to do it when you solve. But I'm going to do it just to show you that these very different rows can be actually linearly dependent and can be some row in our normal common sense. You multiply this by a number and you get this one. Just number is not going to be that simple. I'm going to take row number 1, which is 2 minus 2i, and my second is 2, and multiply it by 1 plus I. That's a number, but not simple number. It's a complex number, right? So what I'm going to have instead of my first element, well, I'm going to write it down first and then actually do multiplication, because if I start doing this at the same time, I think everyone is going to get lost. And the second one is easy to multiply. It's minus 2 and minus 2i. We kind of already see that it looks exactly like the second term here, right? We just need to see is if this expression is going to give us 4 or no. Well, let's just see. I'm going to just multiply it somewhere here below. So I have 1 by 2, which is 2, right? I have 2 by I, which is 2i, right? I have minus 2 by 1, minus 2i, and I have minus 2i multiplied by I. I by I is negative 1, but this is minus is plus, and plus 2, right? These two cancels, and yes, we do have 4. So actually, this expression over here on the top is equal to 4. So we do have that if we multiply this row number 1 by this complex number, we get row number 2. Why I'm doing this? To show you that these are linearly dependent. So you can use either row number 1 or row number 2 to actually continue solution. Minus 2 minus 2i. I will use a row number 1. So I'm going to kind of circle it. I'm going to use a row number 1. To solve, you can use, oh, sorry. So I'm going to use row number 1. So I'm going to write down that 2 minus 2i, sorry, I keep pressing eraser. It's a convenient tool, but I'm not willing to do it. 2 now I need a eraser. Minus 2i multiplied by c1 minus 2 by c2 equals to 0. I'm just kind of trying to solve it. Well, remember that one of the constants is going to be my parameter t. Let me see which one I want to use as t. Well, I think I'm going to use c1 as my parameter. Use c1 as a parameter. And what I'm going to have? 2c2 with minus equals minus 2 minus 2i. And you see, I already missed minus over here. Minus c1. Well, canceling this minus and this minus is going to give me that c2 equals dividing by 2 both sides. It's going to give me minus 1 minus I c1, right? Do I have, let me double check. Yeah, guys, I think I just introduced extra minus, which was not here. I was looking over here and seeing minus 2, but actually this one was plus. Sorry again, just introduced a minus, which was not here. It was no minus here. I should not look here, but should look over here. And then I have to erase some minus from here, which is going to erase the whole thing, right? And there is no minus here either. Okay, now I'm going to create my vector. Let me scroll it up a little bit. So I'm going to create my vector. Vector C is going to be C1, 1 minus I, C1. What is next step? To take C1 outside and have it 1, 1 minus I. Remember what I was doing next. Next, I was finding actually a real and imaginary part, right? Well, I'm going to put it back into solution and then find the real and imaginary part. So my x1 is going to be what? C1, 1, 1 minus I. And no, my solution is, let me scroll down, it's supposed to be RT over here, right? RT, what is my R? My R is 1 plus 2I, somewhere here. So instead of R, I'm going to write down, well, again, I don't want to change the color. So 1 plus 2i, that's my r, multiplied by t. Well, again, I'm going to use Euler's formula. So far, I'm not dealing with my vector yet. Euler's formula is going to give me what? Sorry, it's supposed to be exponential first. E to the power of t, right? If I multiply 1 by t, it's e to the power of t. And then cosine of 2t, this 2 comes from this 2, and I sine of 2t. So that's my first solution. If you wish, you can repeat the procedure and do the second solution and then write down my general solution is like this. But I'm going to separate real and imaginary part and use them as my two independent solutions. So what I'm going to do, guys, I'm going to again bring my cosine and sine inside of this expression. So I'm going to keep like C1 here. And that's going to give me cosine of 2t plus I sine of 2t, right? And over here in denominator, more complicated. I'm going to just like copy them and then multiply them. I don't want to mix up two procedures. Cosine of 2t plus I sine of 2t. And of course, exponential function. And I'm going to simplify my bottom term. So C1 cosine of 2t plus I sine of 2t. It's not going to look very short, unfortunately. If I start multiplying, it's going to give me like 4 terms, I think. So first I multiply by 1. I'm going to, oh, sorry. I pressed something which I should not, I guess, accidentally. like this. Okay, so first I multiply by 1 cosine and sine, right? So I have cosine of 2t plus I sine of 2t. Then multiply by negative I minus I cosine of 2t, and plus I and I is minus 1 by minus is plus. So we are going to have sine of 2t. Looks a little bit crazy. Exponential function is here. And I'm going to separate real and imaginary parts here, right? So real part from the top is cosine, and here cosine and sine. So I'm going to write them down like this. Cosine of 2t and cosine of 2t plus sine of 2t. I'm going to multiply them by exponential function and give them constant c1 plus imaginary part. I'm going to put I over here. And that's going to be sine of 2t. And imaginary part is here. Sine of 2t minus cosine of 2t. Well, because I'm still writing down solution number 1, maybe I should keep the constant c1 here. c1 e to the power of t. But now I'm ready to give a general solution. So that's my real part. This is my imaginary part. Well, I'm going to change this to C2 just to combine two linearly independent solutions with two arbitrary constants. So my general solution, general solution is going to be C1 cosine of 2t cosine of 2t plus supposed to be sine. I started writing down 2t before sine. Sine of 2t e to the power of t plus c2, and my second solution, sine of 2t minus cosine of 2t e to the power of t. These two solutions are totally real solutions. It's going to be a little bit easier to solve initial value problem if you kind of have these two real solutions. And what I'm going to do, guys, I'm going to remember that actually this x bar, it's x1 of t first function and x2 of t my second function. That's a vector, right? So I can write down now that's x1 of t, my solution. The first solution is going to be what? I'm going to copy the top part. It's going to be c1 cosine of 2t and c2 sine of 2t, and I'm going to put exponential factor outside. And over here, x2 of t is going to be a little bit more complicated. It's going to be c1 cosine of 2t plus sine of 2t plus c2 sine of 2t minus cosine of 2t and e to the power of t. Okay, sometimes people are going to combine sine and cosine together and kind of mix up the constants. I'm going to do this, but you don't have to do this when you solve it. I'll understand it without it. But I'm going to show it once, okay? So, for example, if you want to combine cosines together and sines together, it's going to be like c1 minus c2 cosine of 2t. So I combine this one and this one, right? And plus c1 plus c2 sine of 2t e to the power of t. Well, I don't know how really much you need to combine this, but and these are going to be two solutions of my system. Well, what I want to say, you don't have to check linear independence over here. Let me show you what you don't need to do when you solve it. You don't need to check this, that these two are linearly dependent. So they are linearly dependent because we are solving equation to make them really dependent. But if you kind of decide to check it, well, that's up to you. Again, it's not going to benefit solution, but maybe it's going to give you a checkpoint. If you did a mistake finding the second one, you are going to figure it out because they are not going to be linearly dependent, but it's not necessary. Well, again, can you still solve it the standard way? Yes, guys. You can just pretend that complex numbers are like real numbers and you solve it by a standard way. Your solution is going to look a little bit longer if you solve it the standard way, but maybe you will understand it better. And this is a key point, like how much you understand your own solution. If you don't understand, if you solve something but don't understand your solution, maybe makes sense to use the way which you understand, because that's the best way. Okay, that's all about complex numbers. I don't give you more examples because otherwise my lecture is going to be like 2 hours long. You are not going to watch it. So, and that's just going to be like, so I give just 2 examples. I suggest you to solve at least 2 more problems on complex eigenvalues. I know that each problem is taking about 20 minutes to solve, but well, I cannot make them shorter anyway. I don't know any shortcuts. Okay. Okay, guys. So I want to continue complex solutions, complex eigenvalues, and consider initial value problem. Well, I'm going to continue example number 2 for this case. So we remember that we found general solution for example number 2, right? And that was x1 of t, which was equal to c1. Sorry, there is not supposed to be a triangle. I don't know, my computer is doing something weird. I'm not trying to erase this triangle. Erase everything else. Okay, well, it's not like super important. I'm going to just put x1 of t. Maybe I can do it this way. Okay, so let's continue. So we have x1 of t equals c1 cosine of 2t plus c2 sine of 2t, and x2 equals c1 minus c2 cosine of 2t, c1 plus c2 sine of t, and c1 and c2 are arbitrary constants. So now initial value problem. Initial value problem. Well, how it's going to usually look? Well, it's going to be a same problem. X derivative a x, right? We just have some initial values for the vector x1, x2, which is like solution, right? So in our case, I want to consider very simple initial value problem with x1 equals 1 at 0, at time 0, and x2 equals 2. So let's see how do we calculate the constants if we kind of solve initial value problem. Well, basically, it's a very same way. You just plug in t equals 0 into first equation and make it equals to 1. So that's what I'm going to do. I'm going to write down that 1 equals c1. When I plug in 0 into cosine, I'm going to get 1. Right into sine, I'm going to get 0. And exponential function is going to give me 1. So actually, I already have a solution. c1 equals 1, right? For the second one is going to be 2 equals, and here I have c1 minus c2 by cosine. So I'm going to write down c1 minus c2, and cosine is equal to 1, right? And sine is going to give us 0, so c1 plus c2 will be multiplied by 0, and exponential factor is going to give us 1. So basically, that's a system of equations we just solved to find c1 and c2. We basically already do know c1, right? C1 equals 1, and we plug it over here, and we get 2 equals 1 minus C2. And what we should subtract from 1 to get 2? Well, obviously, it's supposed to be C2 equals -1, right? If we subtract -1, we kind of add 1 and we get 2. So we just solved the initial value problem. I'm going to write down our solution and say a few words about the alternative way of solving this system of equations if you don't want to worry about like real and imaginary part of your eigenvector. Well, first let's write down the solution. So x1 of t is going to be equal, over c1 equals 1, so I'm just going to write down cosine of 2t, right? And c2 equals -1, so minus sine of 2t, and e to the power of t. x2 is going to be equal, and we do have c1 minus c2, which is going to be like 1 minus -1, which is going to give us 2 cosine of 2t, right? And c1 plus c2, because they both are equal to 1 is 1 and 1 is -1, we're going to get 0, and sine factor is going to disappear. That's going to be our solution. So this is solution of initial value problem. Now I want to go back and kind of show you how can you solve it differently if you like it. It's not like people are doing it, but you know, maybe. Remember how we were solving the problem. We had a system, right? We found eigenvalue. Then we found one eigenvector which was corresponding to the value 1 plus 2i, and we kind of did not do the second one, which was conjugate. Well, standard procedure, actually, you can go over and just finish standard procedure and find the second eigenvector and give solution in a standard form, like you kind of pretend that the eigenvector is not, or eigenvalue is not a complex number. Actually, for computer system, there is no difference between complex numbers and real numbers. It's going to just process it as a different kind of number, but otherwise there is no difference. So that's what I'm going to do, guys. I'm trying to show you that like initial value problem is going to give you same solution no matter which way you solve general equation. So I'm going to scroll it up and finish this problem alternative way. I'm going to change my color and write down over here alternative way. Well, I'm not going to throw away the solution we already have, right? I'm just going to copy a little bit what we have already and add whatever we are going to kind of have later. So first, the system, just to remind you, the system was looking like this: 3 minus 2, 4 minus 1, x, right? And we already know that there are two eigenvalues, and they are 1 plus 2i and 1 minus 2i. So it's 1 plus minus 2i. And initial values of this problem are, it's not supposed to be equal signs, are, sorry, I'm going to write down as a vector, okay? Equal to 1 and 2. I'm trying to solve actually the same initial problem, but just show you a different way to do this. So we already know the first eigenvector, right? Let me, sorry, my board likes to shrink. So my first eigenvector was x1, and that was what? C1. We already found it in the first part of the solution. 1 minus I, e to the power of 1 plus 2it. Right here, we did not use any assumptions about complex numbers. We just kind of went through the normal general way of solving system of equations. We found eigenvalue, found eigenvector, plugged everything in, and that's a solution, right? So normally we have to do it for the second one. So right now I'm going to search for x2 for the second eigenvector, which corresponds to the second eigenvalue, r2 equals 1 minus 2i, right? Which is conjugate. Well, we already remember that only the first line is going to work. The second line is linearly dependent. Second row, I'm trying to say. So I'm just going to plug in this r into the first line, right? So it's 3 minus 1 minus 2i, that's 3 minus r, and I multiply it by c1 plus, or better say minus, because there is minus 2c2. This part of the solution is exactly same as what we had before, just a different r is plugged in, right? Equals 0, and I'm going to solve it for C2. So C2 from here is going to be equal, right? I'm going to move everything to except C2 to the right side. So I'm going to have 3 minus 1 is 2, right? And that's going to be, sorry, likes choose to play with my board. I don't know what I touch on it. The good thing about Microsoft Whiteboard is like it saves me the whiteboard, not just the file of whiteboard. Otherwise, it's sometimes acting unpredictably. Sorry, I'm going to copy minus 2c2, right, this term, and this one is going to move to the right side. So 3 minus 1 is going to give me 2, so I'm going to put the whole minus in front of the parentheses. So it's going to be 2, and minus is going to give me plus 2i c1. From where dividing by negative 2 everything, I'm going to get that c2 equals 1 plus I C1, which is going to give me general solution or eigenvector. Let me just write it down first as eigenvector. So eigenvector C is going to look like this. C1, 1 plus I, right? And I'm going to take C1 outside just to separate arbitrary number from something which is not arbitrary. And if you compare it to my original vector, I'm going to write it down as vector x2 now, copying this. Well, I'm going to copy C1, but actually we understand that for the second vector, we have to use a different constant, C2. E, and it's going to be e to the power of 1 minus 2i, because we are using this eigenvalue, right? 1 minus 2i t. So that's my second eigenvector. The only thing I want to fix over here or change over here is instead of C1, use C2 to make a difference between these two eigenvectors, because they're supposed to be multiplied by different arbitrary constants. Otherwise, it's going to be kind of my second solution. You see, solution itself is much shorter, right? You don't need to worry about complex numbers. You just kind of deal with them like with normal numbers. Just copy everything and that's it. Now I'm going to write down general solution. Let me scroll it up a little bit and write down general solution. So general solution is going to be a sum of solution x1 plus solution x2. And again, they're supposed to kind of come with different constants. So it's going to be C1, 1 minus I, e to the power of 1 plus 2it, and plus C2, oh, sorry, not supposed to be the power, 1 plus I, e to the power of 1 minus 2it. If you compare these two solutions, they are conjugates of each other, right? Wherever is minus here is plus here, and plus here is going to be minus here. Well, that's our general solution. And it looks like we spend less time on getting it, right? Now, let's try to solve initial value problem. Here you are going to see why people are doing it the first way, not the second way. So for initial value problem, we need to plug in t equals 0, right? Well, that's what I'm going to do. So I'm going to just plug in 0 to solve initial value problem. Initial value problem. I'm going to point it. Well, let's see what we are going to have. Well, first we do have, I don't need the text, we do have 1 and 2, right, initial value. And the second, we just need to plug everywhere t equals 0 into this complicated expression, but not that super complicated. And that's what I'm going to do. So that's C1. And the first part is not going to change. There is no t here, right? If I plug in t equals 0 here, it's going to just kill the whole thing and it's going to turn into like 1, right? So it's e to the power of 0, which is 1. And so far it looks even better than the previous way, right? You will see where it gets more complicated. And again, e to the power of 0 just because it's 0, right? So what I'm going to do, guys, I'm going to combine these two vectors together into like one expression. So I have C1 by 1, right? And C2 plus C2. And for the bottom, I have C1 minus C1 multiplied by I. And the second one is going to give me C2, and C2 multiplied by I is going to give me just C2 multiplied by I. Well, there are two equations, two kind of unknowns, C1 and C2. So I'm going to write it as standard form as two equations. Two equations are going to be 1 equals C1 plus C2, and 2 equals C1. Well, maybe I should keep it like 1 minus I here, and like C2, 1 plus I over here. I don't think that I opened parentheses made any sense right now, opening parentheses in the first line. Okay, now we just solve it. Find C1 and C2 using our initial values, right? I'm going to take the first equation and express, for example, I don't know, C2 from it. So C2 from it is 1 minus C1, right? We'll just move C1 over here. And then plug this C2 over here. So I'm going to move to the right and scroll it a little bit up to see what I'm going to have. So I have 2 equals C1, 1 minus I. Over here, 1 does not look like 1 actually, right? And instead of C2, I put 1 minus C1 1 plus I. Now, guys, we just have linear equation about one unknown, which is C1, right? I'm going to isolate it and solve for it and just find out what is C1 and then find back what is C2. It's going to take me like a little. So 2, I'm going to take C1, 1 minus I, and over here, if I take C1 outside of parentheses, I'm going to have minus 1 minus I, because it had minus, right? And plus 1 plus I, that's just like opening parentheses for this, right? Well, here what I have this one and this one cancel, but I and I is going to be added, right? And if I move this part to the right, I'm going to have 2 minus 1 minus I equals 2I minus I and minus I, right? And C1. Well, if I subtract 2 minus 1, is going to give me 1. 1 minus I equals minus 2I C1. A bit long, but we divide by negative 2I to get C1. So C1 equals 1 minus I divided by negative 2I. I don't want to have I in denominator. So what I'm going to do, guys, I'm going to multiply both numerator and denominator by I to eliminate I from denominator. So I'm going to have I by 1, right? And I by I is negative 1, but negative is going to give me plus 1. And in denominator, I'm going to have 2. 2 is not going to change. I by I is going to give me negative 1, and this minus is going to cancel. So that's what I'm going to have. I'm going to have 1 over 2 plus 1 over 2I. That's my C1. Well, I'm going to take the C1, plug it into C2, and find that C2 is 1 minus C1, which is 1 over 2 plus 1 over 2I, and that's going to be 1 minus 1 over 2 is 1 over 2, and minus 1 over 2I, right? Well, these are two constants, and I'm just going to write them down back into general solution. General solution this way is going to look like this, and I basically already solved the initial value problem, just solution does not look very nice, right? And I cannot compare it with what I had before just because it's very complicated solution. So I'm going to copy 1 over 2 plus 1 over 2I. Here, vector 1, 1 minus I. We're almost done, guys. That's not going to be that long. 1 plus 2I t plus 1 over 2 minus 1 over 2I, 1 plus I, e to the power of 1 minus 2I t. Well, that's actually my final answer. It does not look very nice, and it does not look like a real solution, right? I actually want to check if it's matching the answer which I got already for initial value problem. To do this, I have to kind of simplify it. And that's what I'm going to do, guys. I'm going to simplify my answer. It's going to take me like 5 minutes to do. So what I'm going to do the first, I think I'm going to maybe take e to the power of t and e to the power of t from both terms outside, and 1 over 2 from here and 1 over 2 from here outside. So it's going to give me 1 over 2 e to the power of t. Now here, if I take 1 over 2 from this one, this is 1 over 2, 1 plus I, right? And multiply this 1 plus I by the first term is going to give me 1 plus I here. And the second one, 1 plus I by 1 minus I is going to give me 1 plus 1, right? We remember that it's a square of this and the square of this, which is negative 1, so we are going to have plus. And I'm going to just have e to the power of 2it. I took already this one outside. I'm going to put big brackets. Now, for the second part, I'm going to do the very same. So I'm going to have plus, and again, here I have 1 minus I. So I'm going to have 1 minus I multiplied by 1, and 1 minus I is still going to give me 1 plus 1. E to the power of negative 2it. I'm very close. Okay, now what I'll need to do. I'll need to just kind of simplify it a little bit further. I'm going to copy 1 over 2 and e to the power of t and multiply this e to the first line and kind of combine everything into one vector. So I have e to the power of 2it plus I e to the power of 2it, and then plus e to the power of negative 2it, and minus I e to the power of negative 2it. What I did, I just multiplied this e as a factor by all numbers or all terms in the first row. I'm going to do this for the second one, but second row here, 1 plus 1 is 2, right? So it's going to be much easier. It's going to be 2 e to the power of 2it plus the second one is 2 e to the power of negative 2it. Now, guys, I don't really want to simplify it standard way, these two expressions, but I want to prove a little tiny formula, which is going to help us to simplify it easily. Let me see. Where did I prove it? Okay, I'm going to do the proof in a different color and then use this. So e to the power of ai plus e to the power of negative ai is equal, using Euler's formula, as cosine of a plus I sine of a, right? Plus cosine of a for the second one minus I sine of a. Well, you see what happens. This one and this one cancels, and I actually have 2 cosine of a. So if I have two exponents with like I in exponent and plus and minus, symmetrical, but like plus and minus, it's going to give me 2 cosine of a. Now, if I do have minus between them, ai minus e to the power of negative ai, I'm going to cancel cosine terms and keep the sine terms. Please watch it. I don't want to like use a long way to simplify this expression. So I sine of a minus cosine of a because of this minus, right? And plus I sine of a again because of this minus. I'm just changing the signs here, minus and plus here. Well, now cosine is going to disappear and sine is going to stay, and that's going to be 2i sine of a. Where I'm going to use it? Well, first I'm going to use it over here, guys. Look at this expression. If you take away 2, you're going to have e to the power of 2it and e to the power of negative 2it. We already know that it's going to be 2 cosine of 2t. I'm using this formula, the top one, right? For the first expression, this longer one with 4 terms, I'm going to combine 2 terms together. I'm going to first combine this term and this term. They don't have any I, and they are exactly like opposite, like we have in the top formula. So they will give me 2 cosine of 2t. This term and this term. Now let me change the color, and maybe orange color is not going to be that good. Okay, now I'm going to combine these 2 terms. And you see that if you take I outside, you are going to have exactly like 2it minus 2it. So it's going to be a I by 2 and by sine of 2t. Not exactly the order I have it over here, right? I have 2i here and I put I2, but I'm going to simplify. This one is negative 1. So altogether I have 2 cosine of 2t minus 2 sine of 2t. Again, minus happens because I simplified I by I square. Now I'm going to just write down my final result. And that's going to be 1 over 2 e to the power of t. And on the top I have 2 cosine of 2t minus 2 sine of 2t. And in the bottom I have just 2 by 2 cosine of 2t. Guys, what I'm going to do now, I'm going to take 2 from all these terms outside to cancel this 1/2. So I'm going to have e to the power of t cosine of 2t minus sine of 2t. And here 1, 2 is going to be taken out, but the second one is going to stay 2 cosine of 2t. Well, that's my simplified solution. Do you see that solution is real? Solution is real, right? Now it's time to compare it to what we had before. But to do this comparison, I even don't know how to do this because I kind of have it up, down. But okay, I'm going to write down separately x1 and x2 and then show what we had before. So x1 here is going to be what? E to the power of t, and then cosine of 2t minus sine of 2t. And x2 is going to be e to the power of t 2 cosine of 2t. Okay, now let's see if our solution before was the same. I'll need to scroll it down. Sorry, sometimes I touch something and it's trying to cut it out. Where it was. Not here, not here, not here, not here, not here. Yeah, there it was. Cosine of 2t minus sine of 2t to the power of t and 2 cosine of 2t to the power of t. You see, solution is exactly the same. You see how much more work here in simplifying. So it's less work in getting a general solution. General solution is just much easier than the first way, right? But if you want to get to the final answer, you will need to simplify a lot. And there are many chances to make a mistake, right? That's why people are doing this division of the first eigenvector into imaginary and real parts and using them as a solutions. That's why we want to get it like a real solution from the beginning, because you see, the first way to find the initial value problem solution was just like 2 seconds. You plugged in and calculated the constants almost immediately. Here it took a while, right? Okay, now that's all for the lecture, and let me finish it.